Uh, I'm Swastik Koparthi. I'm going to be talking to you about Turing machines, and yeah, my interests are my research interests are in theoretical computer science, discrete mathematics, finite fields, uh, error correcting codes, and a bunch of related topics like that. Uh, I am interested in theory of computing and complexity theory, both for because of the fundamental nature of the questions that it talks about, and also for the very cool math that is involved in understanding it more. So uh, that's a little bit about me. I'm a professor at Rutgers University in both the departments of mathematics and the department of computer science. Uh, right. I'm going to be telling you about Turing machines, which is a basic model of computation. It is a strengthening of the model of automaton, which you saw already. And it's not just any strengthening, it's such a good strengthening that it captures all forms of computation that we know today. And so this is an extremely fundamental and basic model. We'll spend a whole lectures understanding this model, and many lectures after that will be spent understanding the power of it and what all you can do with it. The Turing machine, so in one sentence, the Turing machine captures what a computer can do. It's a simple mathematical model that can capture what computer can do, and the simplicity of the model enables us to understand it. Okay, great. So that's what this lecture will be about. Okay. So this lecture is about Turing machines. I'm going to start off by defining Turing machines as a slight generalization of a deterministic finite automaton. A Turing machine is supposed to capture what a computer can do, but for now we'll just view it as a model of computation which uh, is given some string as input, and it's trying to determine some property of that string. So, uh, so if you remember what a finite automaton was, it had a finite control, finite state control, and it had access to the input written down as a sequence of letters from some alphabet sigma. So there's an alphabet sigma, and there are some letters in there. And the finite state control uh, goes through this sequence of letters, updating its state as it goes through the letters. And at the end, it makes a decision on whether it thinks the string should, whether it should accept the string or not. A Turing machine is a slightly more powerful version of this. So let me write down uh, some in words what we're going to allow the Turing machine to do, and then I'll state it more formally. So, in words, so a Turing machine uh, has a finite state control too. Has a finite state control. It has the ability to move both left and right as it's going through the input presented on a tape. So the input is presented on a tape. Is presented on a tape, and the Turing machine has a head. So in here, I drew the head as pointing at that particular location, but it can also point at any location at a time. It has a head that can move both left and right. This is unlike a deterministic finite automaton, which can only move right. So it can move both left and right. It decides whether it wants to move left and right based on its current state and what it read. Okay. And finally, it can not only read what's written on the tape, but it can also write on that tape. So, yeah, so this. Okay, so this is one point, another point, and finally, uh, the Turing machine can write on the tape. These are the key defining features of Turing machine over a deterministic finite automaton. The input is presented on a tape. The Turing machine has a head that can point at a particular location on the tape, and at each stage it can either decide to move left or right. And the way it decides to move left or right, it depends on its current state and what it sees written on the tape. Not only that, it can also decide whether to write something. At every stage, it can decide whether it wants to write something down on the location currently on the tape. So it can, so it can write things down. So that's what the Turing machine can do. So there's one final aspect which I haven't said yet, which is that this tape is infinitely long. Okay, so the Turing machine has the ability to not only overwrite what has been written on the input, but it can also write things beyond that. And so it has access to a lot of memory, so to speak. Okay, so let me also, and that is the fine set. It's presented on a tape which is infinite. In that direction. Okay, so now I'm going to state things slightly more formally. So just like in the deterministic finite automaton case, there is a set of states. There is a start state. There is the alphabet sigma over which we're working. Strings from this language that we're, strings, the input is expected to be over this finite alphabet. So it's a finite alphabet. This is also a finite set of states. Finite alphabet. There's also a tape alphabet. The tape alphabet. Oh, the tape alphabet is the alphabet uh, which is what can be written on the tape. So it's a this is a finite, yeah, for finite alphabet for the inputs. This is the finite tape alphabet. Automatically, since the input starts off on the tape, we assume that sigma is contained in this. And what's more, there's a special tape symbol called blank. That's also an element of gamma. There's the blank symbol that's also in gamma. And we assume that the Turing machine starts off with the tape have be containing the input, followed by infinitely many blanks. Good. Then there's also a special accept state, Q accept. There's a special reject state, Q reject. This is a state where the Turing machine can decide, okay, I've decided to accept the string, I've seen enough, it just jumps to Q accept. And at that point, the Turing machine halts and the string is accepted. Similarly, it can decide that it wants to reject by just moving to the state Q reject. Okay. And so the accept, special accept state, special accept and halt state. And this is a special reject and halt state. And the killer piece is the transition function. This is what up how the the Turing machine updates its state, updates what's written on the tape as a function of its current state, what's currently written on the tape, and how it moves its head based on all this. Okay, so this is delta, the transition function. What does delta take as input and what does it give as output? Okay, so following what I said, it's a function of the current state and what's currently written on the tape, and then it decides what state to go to, what to write on on that current location of the tape, and whether to move left or right. So it is a function, delta is a function that maps, it takes a state and an element of the tape alphabet, and it outputs the new state, what to write in place of what was already written in that current location of the tape. So if it's choosing not to touch what was already written, it will just simply copy what's written here into this. Its output tape alphabet symbol will be the same as the input tape alphabet symbol in the special case when it's not writing anything. And it also tells uh, the Turing machine whether to move the head right or left. So it's to left or right. These seven items, Q, Q0, so the set of states, the start state, the finite alphabet for the inputs, the finite tape alphabet, the special accept state, the special reject state, and the special transition, and sorry, not special, the transition function, which governs how the Turing machine works completely. This seven tuple is the formal definition of a Turing machine. Yeah, so let's write that down. A Turing machine is a seven tuple Q, like sigma, gamma, Q naught, oh, maybe delta next. Delta, Q naught, Q accept, and Q reject, as above. This is the formal definition of Turing machine. It's a very compact definition of what it means to compute. When we think about how we compute, we're heavily distracted by the fact that our brains can store so much. I can think of a number from 1 up to 10 to the power 15 and remember it. And I can give it a name and I can walk around saying that number to other people. But but that's a bit of a distraction. If I only had a teeny tiny bit of memory, I can only store 7 bits of memory in my head, then my mind is like the finite control of the Turing machine. Anyway, it's like the finite control of a Turing machine, but it's just a big finite, and maybe we are distracted by the fact that it's so big, and we think, oh, maybe it's infinite. No, it's not. It's finite. Good. So if you have finite memory, then you're like the control of the Turing machine. And even if you have a finite amount of memory, you can go around doing computation on very big things. You can have an extremely large number. Oh, okay. So I can add two 100-digit numbers. How do I do it? I don't take the first number and remember it in my head and then do some special magic involving that big number. What I do is I follow the elementary school algorithm for addition. I write the first number out, I write the second number out, one below the other, aligned properly. And then I do a very, very local computation where I say, okay, there's a 7 here, there's a 3 here, 7 plus 3 is 10. So I put a 0 down below and I put a carry of 1. And I take the carry and I take another digit, and I do some local computation involving that. And I write something down here and I write something down here. And I just do all kinds of writing things all over. I don't ever have to sit and memorize the whole number and do things based on that. I do computation, or sorry, I look at what's written. I move around based on what's written. I sometimes, to help myself, I jot down some marks and symbols around, like the carry, and that's how I add very large numbers myself. I'm basically using a finite amount of state and marking things on on the paper in front of me, and I execute some simple routine again and again and again based on this finite amount of state that I have. That's how I do my computation. And Turing machines capture the fact that all computation is basically, or not all, the Turing machine model captures all computation that can be done using this process, namely looking locally at what's been written right now, maybe what's currently written down at a particular location, maybe making some extra marks on the side to help you do some further computation along it, and writing things down. Okay, so that's what the Turing machine model is. It's a harmless looking model, not that much different from the deterministic finite automaton, but it turns out that it's capable of expressing every single algorithm uh, that we do, that we have come up with, and that we think about. And in a later class, you will learn about the Church-Turing thesis, which is uh, it's not a theorem; it's a thesis, which means yeah, I don't know what it means, but okay, which says that uh, we believe that all computation is captured by this model, the Turing machine. Okay, so just before we go on to do uh, more things with Turing machines, any questions? No? Okay, great. So then we move on. Okay, so what I'm going to do now is give an example of a Turing machine. So unlike deterministic finite automata, nobody ever specifies a Turing machine through the 7 tuple. Any reasonable Turing machine for even a slightly complicated problem is going to be so humongous and so complicated to describe in this extremely formal language. We have to resort to describing in words what the Turing machine does. So I'm going to do that soon. I don't know if you'll exactly see the proof of this, but it will be stated that anything that can be done in a classical programming language can also be done by Turing machine. So if you want to describe a Turing machine that does something, you just have to specify it in a high level programming language like C or something. Okay, so I'm now going to an example of a Turing machine. Okay. Okay, so actually, let me say something. So, anyone can define a Turing machine. A Turing machine that does something interesting, that's the tricky part. Okay, so, okay, scratch that. No example of Turing machine. What does it mean for a Turing machine to do something? Okay, so associated to every Turing machine, we look at the language of strings that it accepts. Okay, so the language, so language of a Turing machine M is the set of strings accepted. The set of strings accepted by M. When is a string accepted? Well, if during the execution of this Turing machine on uh, on that string as input, Yeah, so it's doing something, computing. At some point, it decides, okay, let's move to Q accept. At that point, it halts and accepts. So those are the strings, the set of strings accepted by him. That's when it can accept a string. It may not accept a string. It may decide at some point to reject, at which point it's not accepted. Or it may just keep moving from state to state to state, writing, updating, doing its own computation, and never entering the accept state. In this case, we don't say the string was accepted. In this case, the Turing machine went into an infinite loop when that string was in it. Okay, so just for just to understand exactly what the possibilities are on a given input x in sigma star, m may either one is halt and accept, to halt and reject, or three go into an infinite loop, which is not halt. So go into an infinite loop suggests that it's just doing the same thing again. Okay, let's say that uh, loop infinitely, and that is it doesn't halt ever. These are the three possibilities for what happens when a Turing machine is fed an input x. We only in case one do we say x is in the language of the Turing machine M. In both other cases, we say x is not in the language of the machine. Okay, so this is the set of strings accepted uh, by Turing machine M. So this is the language of a Turing machine M. It's also called the language. It's also called the language recognized by M. This aspect, that there's an infinite loop possible, this is unique to the Turing machine case. In the deterministic finite automaton case, the automaton just read the input left to right. At the end, it was done. Now, since we give the ability to move both left and right, and also give the ability to write things and write all the way across the infinite on the entire infinite tape, this extra possibility of infinitely looping arises. This is unfortunate, but it's almost unavoidable. You can define other versions of okay, I don't know what you mean by unavoidable. I take that back. Yes, you can define other models of computation that don't have this infinite loop feature, but then those models are weaker than what Turing machines can do. Turing machines are more powerful than all those. And the goal of Turing, while defining Turing machines, uh, was to define a model that captured every possible procedure for computation that 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 people can do. Okay. Yep. So now let me give an example of a Turing machine recognizing a nice language. Okay, so that's okay. So I'm going to start with an example which we studied in the deterministic finite automaton section of this course. It was a language which cannot be recognized by deterministic finite automaton. I'm now going to show that this language L is Turing recognizable. This is the language of a string W, sharp W, where W is a string in 0, 1 star. This language is easily seen not to be regular. But we'll see that the extra power in the definition of Turing machines allows Turing machines to recognize this language. So I'm just going to describe this Turing machine to you in an informal way, telling you what the states of the Turing machine represent, and I'll just say it informally. Everything I say can be translated into a formal specification of what the set capital Q is, the set of states, what the transition function delta is, and all that. So everything I say can be easily translated into a formal specification of a Turing machine. Humans can't really understand each other if they talk in formal language specifications of Turing machines. So the high level idea that I give and you receive is the more important part when you design a Turing machine. Later, you will see, as I said, that everything that you can do in a standard programming language can be done by Turing machine. So uh, later, after you've seen a little bit more in this course, you can just specify a Turing machine by writing a program in a high-level programming language, and that specifies something that a Turing machine can do. Okay, so for this language L, let me just describe how a Turing machine would recognize this language. So it expects on its tape, it expects to see some string W. Okay, so that's a whole bunch of cells there of the tape. Then there's a sharp symbol, and then it expects to see another whole bunch of W's. And then after that, it expects to see blank, blank, blank. The rest of the tape should just be full of blanks. There should be nothing else on the tape. It should just be W sharp W. That's what we expect the Turing machine to see. So what the Turing machine is going to do is the following. It will start off at the beginning. It will mark. Okay, so it's going every letter that it sees before the sharp, it's going to try to mark it off against a letter that it sees after the sharp. Okay, so the tape alphabet, this is already going to give a big hint about what it is going to be sigma. So that's 0, 1, sharp. Okay, it also has to have blank because that's always the case. Good. And then there's more, so it's going to be a marked 0. This is a special character which means which is going to mean there was a 0 in the input in this location, and I've already seen it, or I've already accounted for it. That's what the mark on top means. Sorry, it means in the sense that that's what we interpret it to mean when we design this Turing machine. So 1 dot. Okay, I think that'll be enough for this. If not, we'll go back and modify. Okay, so this is the tape alphabet. The way the Turing machine works is, okay, so it goes to the first symbol written here. Let's see. It goes to the first symbol written here. It sees that's the first. The head starts off at the beginning of the tape. Whatever it sees there, it knows that say there is 0 or a 1. Oh, okay. Okay, this is some special case if it's already a sharp. Okay, but okay, so if it's 0, then it will replace that 0 with a 0 dot. If it's a 1, it replaces that with a 1 dot. If it's a 0, it also goes into a special state, which means I just saw 0 on the left hand side. And then it moves all the way from here, keeps moving right until it sees sharp, after which it expects to see the same letter that it saw in the very beginning. Okay, so that's what we're the intended execution of this Turing machine on a string that's legal, that is actually in the language, is that it's going to mark letters which are on the left of the sharp against letters on the right of the sharp. So it will see a letter here and then keep moving to the right. Once it sees the sharp, it will keep moving further to the right, crossing all the letters that it has already seen. How does it know it's seen a letter? By the dot marked above it. Okay, so I'm going to write this now in words. Okay, so We start off. So this is step one is mark the first. Okay, so if the first letter, no, the first, if the letter under the tape, letter under the head is 0, replace it. We're assume so the step one is when we're going to assume we are looking at the first unmarked letter to the left of the sharp sign. If the letter under the head is 0, replace it with 0 dot, move into state I saw a 0 on the left of sharp. Yeah, good. So it moved into that state, and okay, that's one. Okay, that if the letter under the head is 1, replace it with 1 dot, move into a state I saw a 1 on the left of sharp. That's another state. These two states have, how does the Turing machine behave when it's in one of these two states? If it's in this state, the way it's going to behave is keep going right, just keep going right until you see, so if, yeah, until you see a sharp. After you see a sharp, keep going right. That means once you see a sharp, then you move into another state, which means I saw a 0 on the left of sharp and I also saw the sharp, and keep moving right some more. Keep moving right until you see an unmarked 0 or 1. At that point, check that the first unmarked 0 or 1 letter on the right of the sharp is the same as is a 0. Okay, so let me say that again. If you just saw a 0 on this side of the another picture. This is the tape. There's lots of blanks at the end. Okay. The sharp, and there are lots of characters here, and then lots of characters here. And in an intermediate state of the computation, some of the letters here are going to be marked with dots. I'm writing X there. It's going to be marked with dots. And good. That means that they have already been seen, and this has already been seen. And if you haven't already gone into, if at any point you find some character on the left of the sharp does not equal the corresponding character on the right of the sharp, we are just going to reject state and reject outright. And yeah, if that hasn't happened yet, then you just keep going to the left of the sharp and then back to the right of the sharp, to the left of the sharp and back to the right of the sharp. The Turing machine is moving around a lot. It's a busybody. It keeps going left as much as it can to the first character that is not marked. How do you find the first character that's not marked? You go to the first character, you keep going until you see a character that's marked, and then move right, and then you know that you're at the first character that's not marked. So that's how you find what the first character is. The first unmarked character is on the left of the sharp. Then you start moving to the right. You wait for the sharp. You should see only one sharp. Then you keep going to the right. You see a whole bunch of marked letters. You don't have to do anything about them because they were already taken care of in previous executions in the previous part of the execution of the Turing machine. Keep going right, and finally you reach the first unmarked character on the right of the sharp, and then make sure that what you saw there was what you saw there. Okay, good. Now we are okay, so we keep doing this, moving left and right until at the very end, uh, we keep doing this, moving left and right until at the very end we have made sure that all the characters on the left of the sharp are matched by all the characters on the right of the sharp. So at the end, we check that there are no unmarked characters uh, on either side of the sharp. So Sipser's textbook has a bunch of examples of uh, Turing machines for doing specific things in written out in elaborate detail. Uh, I highly recommend looking at them. So this Turing machine did not really use the power of the infinite tape that is available. It only worked within the space used by the input, but it did use the power of an expanded tape alphabet. Uh, Turing machines can use the power of this extremely long tape, using that to store intermediate computations of things. Uh, right. So this small example this is just a small example, just using one tiny aspect of how what Turing machines can do. They can actually do anything that a high level programming language can do. Okay, so this is the end of video 1. I'm now going to, in the next video, we're going to talk about uh, Turing. So we define Turing recognizable languages. We're going to talk about another important notion, the notion of Turing decidable languages, which are those languages that can be uh, for which a Turing machine can take a string and tell you whether that string is in the language or not after halting for sure. This is opposed to the current definition of Turing recognizable, where we give Turing machines the option of going into an infinite loop. Such Turing machines, I mean, they are nice. They do recognize languages in a certain sense, but these are not something that you'd want to call as a subroutine while doing something else, because they may just go off into an infinite loop if their input presented to them is not if the input presented to them is not in the language. So uh, we'll talk about this important notion of Turing decidability, and that would be the topic of the next class. Okay, thanks.